Welcome, everybody. This is lecture 24 of CS267, Applications of Parallel Computing and Parallel Computers. We're pretty close to the end of the semester. There's one more week to go. We're going to go over next week in computational cosmology as well as biology in different lectures. And that's going to be the end of lectures. And you know, after that, we have a week of poster presentations, which we do not expect your projects to be complete at the time. So if you're stressing about that, please don't. We want your projects to be complete by the final report time, which is a few weeks after that. But we do want to get a sense of your progress and the concrete goals of the project you're working on and so on by the poster session. So let me start by giving you a short outline of what we're going to do. We're going to go over something that seems not all that related, but it's going to come up so often throughout the lecture that it's handy to review, which is a method of solving recurrences. In fact, it's not even a method. It's a summary of a theorem applied in many cases where there's a recurrence. And then we're going to go over searching and then sorting in shared memory and sorting in distributed memory. And we're just going to choose one representative algorithm per problem instead of doing a long laundry list of problems. But know that we're going to give references to other relevant work in this domain. It's a very well-studied problem or problems. So there's no shortage of algorithms or implementations of especially sorting in distributed memory or shared memory. So what is the master method? It is really for solving a recurrence of the following kind. You have a problem of size n, and you're dividing this to subproblems of sizes n over b each. And there are 8 such subproblems. And the cost at each level of recursion is a function of n. And this might be the cost of combining, the cost of splitting. We're not specifying what that is. Okay. And the general idea of the master method is simply to compare the cost of the work that's done at each level of the recursion, which is the function of n, with this quantity n to the log base b a. And remember, b is what is the factor that I'm shrinking my problem size, and a is how many subproblems I'm creating. And intuitively, you can think of it the following way. If I was dividing my problem into 2 subproblems of half the size of the original problem each, then this quantity would be n to the log base 2, right? And that would be n, right? So, and that makes sense if you think about the recursion tree, about how many work is generated throughout the whole tree if there was no cost of combining. So that's basically going to be the main idea, and it's going to intuitively make sense as we go over examples. So the first case is when this quantity n to the log base b a is significantly larger than the cost of combining, in which case the recursion will solve and the solution of the recursion will be dominated by the number of subproblems we're creating, not by the cost of the extra work we do to combine or split the data, right? And then the actual, I mean, there's of course the mathematically, what do we mean with significantly larger than? It is an asymptotic meaning for some constant epsilon. The fn should be actually equal to n to the log base ba minus that epsilon value for some positive epsilon. And the solution in this case will just solve into n to the log base ba, which means that you can ignore the cost of the splits and combines and just look at the number of nodes in the recursion tree if you have materialized all of it in your mind. It doesn't need to be all at memory at once. And that's just going to be the total cost of the computation. The second case is when they're more or less equal, or more specifically, that the cost of combining is n to the log base ba times some polylogarithm which means log n to the power of some k. And this k can be 0, meaning that doesn't exist, that log n term, but it can have it accepts a bunch of logarithmic terms, and which is okay. And now think about the following case, where, for example, you're again dividing your problem into in the recursion into 2 subproblems, each of them are of n over b size, in which and the combination, the cost of combining them is order n. Well, that makes at that moment you're looking at a problem that, okay, I am creating 2 subproblems, and I have a cost of log n to combine and split them. And as you go progress in the tree, recursion tree, at each level, you're going to have a cost of order n total. And the depth of the recursion tree will be logarithmic because of the way you're dividing it by half. And what do we expect? Well, we just need to, because the cost of the extra operation is order n, and you have log n layers, then you expect something like n log n time, which is essentially a general, this theorem is a generalization of that simple observation. If they're more or less the same, up to polar logarithmic factors, then this solves into n to the log base b times, again, polar logarithm of n, except now the power of the logarithm is 1 up, right? If there was no logarithm, then a logarithm appears. If there was a log to the k, now it becomes log power of k plus 1. Just exactly the quicksort recursion that I described without the formula is written at the bottom. And the final case is, of course, the word is symmetric in many cases, which is this case where the cost of combination dominates. And more specifically, it also means that the cost of combination is at least, which is the big omega notation, at least n to the log base ba plus some epsilon that is positive. And in this case, the solution will be basically dominated by the Fn. Again, the polar logarithm doesn't count. It needs to be asymptotically larger. Fn needs to be asymptotically larger by a non-logarithmic factor. Summary, whatever is larger dominates. If n to the log base ba dominates, then that's the solution to your recursion. If f of n dominates, that's the solution of your recursion. If they are equivalent up to polar logarithm factors, then you get n to the log base a times the polar logarithm where the power increases by 1. All right, let's start with searching. And I'm going to start, instead of diving into distributed memory or shared memory parallelism, I'm going to start with a serial algorithm, because distributed memory algorithms will be somewhat easier to describe once we understand how to choose a particular element from the data in terms of their order. So the selection problem is finding the kth smallest element in a list or array of length n. It's known as an order statistics in general. You can define equivalent questions, find the kth largest and whatnot. But the common case is find the median. We're going to describe the algorithms for finding median, I say. But you can use the same idea to find the kth element very easily. So the quick select algorithm is like the quicksort for those of you who are computer scientists, but recurses only on one direction. For those of us who are not those of you who are not computer scientists, quicksort is basically the following algorithm: pick a pivot, any pivot randomly, any element in the array, and then divide your array into 2 sets. The half of them are smaller than the pivot, half of them are larger or equal to than the pivot, and recursively call the safe ones. That's really quick sort. And quick select is very similar. Instead of recursing on both directions, because I only want to find the kth element as opposed to getting a sorted output, I only need to recurse on the side where the element that I'm looking for lies. So simply, I'm just recursing on one direction. But just like quicksort, quick select has a worst case complexity of n squared. On average time, it works beautiful. but there is no way to prove. In fact, you can prove that there's adversarial pivot selections that's going to make this algorithm run n squared. And if you're unlucky, like many of us, who called quicksort in an already sorted data, where the implementation chooses the first element as pivot, you might be wondering why your algorithm is taking hours on a large data set, because it suddenly landed to be the worst case complexity and n squared. It happens actually more often than you think. So how do we solve this? A simple algorithm, or in retrospect, a simple algorithm. At the time, I'm sure it was not simple. By these 5 people, 4 of whom, no. What do I say? Oh, okay. So the reason I say 6 total is because quick select was invented by Hoare, and the median of median algorithm is invented by these 5 people. So we're looking at 6 names here in this slide. And out of that 6 names, I'm going to answer instead of waiting, because this is not a live classroom. 5 of them already have Turing awards. So that's a very famous group of people who have worked on this problem. And the median of median basically is based on quick select, but in a way that it chooses the pivot, it guarantees worst case linear time. And it will tie into a parallel algorithm. So let's start with the algorithm description. We divide our list into, let's say for concreteness, we're going to divide it into sublists of 5 elements each. So there's going to be n over 5 sublists. And this 5 number can change, but it cannot be smaller than 5. And you'll see why it cannot be. The range it can be chosen is actually pretty tight. I think 7 still works, but I haven't worked out all the numbers. 3 doesn't work. And 4 is tricky because it's not an odd number. What does it mean to be the median, right? So sort each sublist and find their median. And then find the median of the medians, right? And then recursively call it. Okay, that looks a little abstract, but with a picture, it's much easier. So I have all these lists. Each one of them has 5 elements, and I found the medians of each one of them. Remember, we don't need to sort the lists. So I'm not arguing anything about the order here. All I'm saying is these 2 elements are smaller than the median here. These 2 elements are smaller than the median here, but the shades are kind of misleading. These are not explicitly sorted. This can be in a different order. And what I'm also saying is this middle element is the median of medians, meaning it's the median of all these things that are inside this lavender box. And also they're not explicitly sorted. It's just the median, meaning that any element here is smaller than the median of medians, but these lists, the medians are not necessarily in a sorted order. So I found the median of medians among the sublist of among the medians list, which is of size n over 5. Now, what can I say? I can say that any element in this box on the top left, let's call them A prime, is smaller than the median of medians. Well, why? Because every single median that is to the left of the median of medians is by definition smaller than the median of medians. And every element that are smaller than those medians are smaller by transitivity from the median of medians. So that's very simple. And by symmetry, everything in this bottom right box, the C prime, is larger than median of medians. So I have two good statements to make. And what are the sizes of these boxes? Well, I claim the size of box A prime is at least 3 over 10 of the original list size. And that's also simple to see. Why? Because if I looked at this whole big box, if I extended this box to include the whole thing, it would be 3 over 5. And since this is less than or equal to mm, then it should be at least 3 over 10. And the same argument applies to C prime, which means that the number of elements there is 3n over 10. We don't, as I said, we don't know the order, explicit order of these medians. We haven't sorted them, but we only know which one is, whether they're smaller or larger than the median of medians. I don't care the relative order between this gray box versus the blue box. Okay, so now all we want to do is recurse. We partition our elements into 3 sets. One is those that are smaller than the median of medians, and those that are equal to the median of medians, and those that are larger than the median of medians, right? And these will be so the tricky part here is the A prime that I showed you here is actually a subset of A that I define here, right? And so on. So here's the code. I divide and sort my lists of 5 elements each, and I recursively find the median in a list of size n over 5, and I partition my data based on that median of medians into 3 sets as is defined in the top, A, B, and C. And now I'm just going to recurse on A and C, and if I found the solution, I'm done. So that's basically the main idea. Why do I say the set of elements that I'm recursing on A is potentially larger than A prime? Well, because all I'm saying is, on the previous slide, sorry, wrong direction, everything in A prime is smaller than MM. It is possible that there are elements here, outside this box, or there, that are also smaller than median of medians. And my partition function will put them in the correct place. I just cannot prove anything about the cardinality of these elements outside the boxes. So the A is larger than A prime, potentially, but I can't prove that. And I can't prove the cardinality. So I'm just going to base my analysis on what I can prove. In practice, it's going to be actually a better bound. That's all I'm saying. All right, then I'm recursively calling this function. So what is the complexity? The complexity is the following recursion. I start with a problem of size n. I create a subproblem of n over 5, which is the list of medians that I need to solve. Plus, then I'm successfully discarding at least 3 over 10 of the data, because I either recurse on A or I recurse on C, and I know that A or C, one of them is at least 3n over 10. Both of them actually are at least 3 over 10. So since I'm only recursing on one of them, my recursion has 7 over 10 here. And the cost of combining is due to the partitioning. Sorry, the cost of partitioning the data due to the function that partitions in this line, there's a linear cost. Okay, exactly what I said. Remember the same function. So how do I solve this? Well, this is 9 over 10 n plus order n. The master method comes to my rescue, and I look at the n to the log base BA, which is smaller than Fn, which is the cost of combination. And therefore it solves to order n, then done. This seems very simple, right? So why did I choose the list size to be 5? Well, if I chose the list size to be 3, you'll see that this summation is not gonna actually be smaller than order n. It barely became smaller than order n, the cost of partitioning. There was a reason we chose this to be 5. And I believe, again, 7 probably works, but I'm gonna leave it to as a homework for those of you who are interested. Okay, now that we know the median of medians serial searching algorithm, how can we use it to come up with a parallel Kate element pick algorithm? Well, how can we can just say that each processor computes its local median, and now we can find a global median of medians, discard the elements, and recurse. Seems good, except that I have no guarantee on how many elements are going to be discarded at each processor. Because it's possible that the global median of medians is not all that balanced. If the initial data is close to sorted, as opposed to being random values, then it's quite likely that each processor is going to discard a disproportionate amount of data compared to each other. So you get into a load imbalance situation, and how these authors, Bader and Haha, solved this problem was to redistribute occasionally the data to guarantee load balance. This is extra communication, extra programming hassle, but has a good bound. It works fine. And then you have to keep track of the original data and bring it back. So it's a little painful to implement. And can we get away without redistribution? So that's the algorithm I'm going to describe. Is there a simpler algorithm that doesn't redistribute for load balance? The idea is simply to ignore the load imbalance instead of dealing with it. So far we have been using the exact median definition. What if we use this weighted version of the median definition, which is the math is simply, let's say you have P distinct elements, M1 to MP, and each one has a positive weight associated with it. And the weighted median is such that if you had sorted them and you were summing up the weights, it is the index at which the summation of the weights for W0, W1, W2, W all the way to the median that we're dealing with is equal to 1/2. So I'm associating a weight with each element such that the sum of the weights are equal to 1. And if I had sorted them, again, I'm not sorting them, but if I had sorted them, the sum of the weight up to that ith location would be at least 1/2. So I choose that index I as my weighted median. You can see that this definition actually generalizes to the basic median, in which case every weight is equal to 1/p, right? And that's this, you'll be choosing the right median with that equal weight. And it's going to be obvious why this algorithm works. And this has been invented by 2 different people 4 years apart, which is a little odd, but in any case, here's how you can do this. We can distribute the data, first of all, so that each processor owns N/P of the data. And everybody finds their local median. And then we then all gather, we exchange these medians. So this data size that is gathered is order P, because every processor has only one median of their local data. We're computing the weighted median redundantly. We can have one processor do it and broadcast that value. It's not going to change the complexity. We're doing this redundantly. And then since we redundantly computed the weighted median of medians, we don't need to rebroadcast. Everybody can partition their local data serially, or any single node parallelization is fine here, to this same sets A, B, C, which are the data that's smaller than the weighted medians, larger than or equal to, or larger than and equal to. And at which point we figure out the cardinality of these set of sets. We either find the solution we're looking for, meaning the kth element in the list we're looking for is in the range, meaning it is the value k in the order is larger than the cardinality of the set that is smaller, and it's than the weighted median of medians we chose, and it's less than or equal to this number of elements smaller plus the number of elements that are equal. So remember, this is more than one value satisfies this, because it's possible that there is repeated elements in the data, and the kth element can be any one of them if they're equal. Or we recurse in one direction or the other. right? If it's if the Kate element we're looking for is Kate order is smaller than the cardinality of the set, that's smaller than the weighted median of medians, we recurse left. And if the value K, the order K we're looking for, is larger than LS plus equal, then we recurse on the right. It's a complicated algorithm to get correctly, actually. I'm gonna have to confess that as someone who worked on this, but it's pretty elegant. All right, so where do we get 3n over 4? It's basically by definition of weighted median, right? Remember, the weights up onto that ith index sum up to 1 over 2. Now, I am replacing weights with the number of elements in each processor. So the way I'm using weights here is that after the initial iteration, every processor will have a list of entries, but those list cardinalities will be different depending on how many elements have been discarded in previous iterations. And what I'm saying, if I have a list that is small, then its contribution to the weighted median of medians is smaller. And if you look at the math at processor I, the number of elements that are smaller than that local median is at least ni over 2, which ni is the cardinality of that set at the moment by the definition of median. And we know that half of those elements have to be smaller than the actual median of medians. So the total number of elements that are less than or equal to the weighted median of medians is just n over 4. And the other case is symmetric. And for those of you who are looking for a visualization, it doesn't add too much value, but you can look at this 4 list, which I intentionally drew them as if they are out of balance at this point. It's somewhere in the iteration. Every processor has a different length list. And what we're guaranteeing with the weighted median of medians is the thing that we're discarding is 3n over 4. Notice that this is actually a slightly worse bound, very slightly, than the serial case, which was 7 over 10. But that's not all that big deal. And one of the reasons it is because we can stop in a different place. So if a lot of the lists that are on the left side after I sorted them are small, like really small lists here, then the weighted median of medians will be all the way to the right. And the algorithm would still actually work fine, meaning instead of being the n over second list contributing to the weighted median of median, all the way towards the end of the list, something like that will contribute. So let's try to solve this. The recursion boils down into, I'm going to solve it initially for the communication cost, and we're going to go back to the computation cost. The communication cost of finding the Kate element on a list of size n, and I'm not using the word k in the complexity because it's the same complexity for any k. So you can find any Kate order element, Kate smallest element with the same algorithm, is less than or equal to the communication cost of 3n over 4, because of the recursion, we're getting rid of 1 over 4 size, plus this complexity of one latency term of log p, and log p comes from all getters and reductions, plus order p, because I need to gather the medians list so that I can find the weighted medians. And that's all. So when I solve this, I get this wonderful solution down there. And why do I get this wonderful solution? Again, the master method. Simply because when I compare the cost of combination versus the base case, the cost of actual work that's done at each level dominates, so I get a log n term. So can I do a little better? I can. We can coarsen the base case and not get a reasonable impact on the asymptotics. Instead of solving the problem all the way to the bottom of the recursion tree, we can basically stop the recursion when the remaining number of elements are n over p. So when the elements are down to all the way to n over p, then one processor gathers them and locally sorts them. And why is this asymptotically better? I'm not claiming it's going to be better in practice. Someone needs to experiment. The number of recursive calls will go down from log n to log p, because I'm stopping early. You can do the math there. Extra bandwidth to gather is n over p, but that's a cost that I'm more or less willing to pay. That's the argument for coarsening. And how about the computation? We have so far only bothered with the communication cost. The computation is sadly, or maybe not sadly, this is actually going to be very little impact on the runtime. The runtime will be mostly determined by the communication cost, like in many other problems. But what I cannot prove is that the lists are shrinking in size. Remember, I have no way to guarantee that my lists are shrinking, local lists are shrinking in any reasonable size. Globally, I am discarding a quarter of my data at each iteration of the algorithm. But for a particular list, I might not be discarding anything, depending on how adversarial the input set is. For that reason, at each layer, that I might be just doing n over p work. And I have log n layers, so n over p times log n would be the computational cost overall. And that's basically what I just said. We can't guarantee that the local lists are going to shrink. And at the end, we might be left with a list of size n over p, and then I have to sort this list at the end locally. But the algorithm is, I think, very beautiful and uses the ideas of median of median selection. There is better versions of this algorithm in practice, which are randomized. When the lecture was designed originally, it was at a point in the year before the spring break, I think, that I was able to talk about potential class projects, but it's too late. Unless someone really urgently needs a different class project, you can certainly evaluate some of these algorithms. But I think this lecture is coming a little too late for this year. I don't see any questions, so I'm going to dive into the sorting section of the lecture. And I'm going to start with shared memory. And for that, the algorithm we're going to go over as our example is merge sort. It's an example of a recursive sorting algorithm, just like the quick select and median of median selects were recursive. And it's based on, similarly, most recursive algorithms based on divide and conquer. It uses the merge operation. Anyone who has taken data structures probably knows about this, but I'm talking more to the non-computer scientists. The drawback of merge sort is that it's really not in place. It needs two arrays, but that's not a big deal in the grand scheme of things. So here's the algorithm. You're basically just streaming through inputs A and B, and whichever one of the elements from that list at the moment is smaller, you copy it to the output, and it increments its pointer. It's as simple as you might guess. And I'm not going to play this animation. The merge is very trivial, as you would imagine. So how can I use this merge routine to come up with a sorting algorithm? It's also very simple. In fact, I'm going to put the parallel lines here, but you can so far ignore the parallel lines initially. What I'm essentially doing is I am recursively calling merge sort into smaller and smaller arrays, which will obviously at the base case come up with a sorted list. And at that point, the recursion will start collecting back and will call merge for every sorted list. So I am calling merge sort recursively on half the size of array and a quarter size and 1/8. Then I get, of course, at the base case, what I consider as merged lists. I can coarsen this thing, and I don't need to recurse log n layers, technically. I can coarsen the base case to do a fast sorting for small n, like an insertion sort when but for illustration, let's do it the algorithm in pure way. And at that point, I'm just merging, pairs of 2. And the recursion will collect back, and it's going to merge lists of size 2, lists of size 4, and we're done. Okay, so what's the work here? Meaning, if this was just serial, the work would be, I have a problem of size n, I'm creating 2 problems of size n over 2 each, and I have a cost to merge them, which is linear. Well, we know from the master's theorem, it solves to n log n, the basic case. But what about the so-called span? Span, for those of you who remember, or maybe we didn't talk too much about this is called the critical path. If I had infinite processors, how fast I can run this algorithm? Or alternatively, if I looked at the dependencies of the tasks I have, what is the path that is longest from the beginning to the end, right? Throwing more parallelism is not going to accelerate that critical path because the task graph doesn't have enough parallelism. So span, meaning the time it would take to solve this problem at infinite number of processes, meaning you're not bound by the processing parallelism, you're bound by the critical path, is simply you have a problem of size n, and because you're assuming infinite processing power, the recursion doesn't have a extra factor 2 in front of it. You're basically creating 2 subproblems, and you're just dedicating half of your infinite processors to one of them, right? So it's the factor 2 doesn't come into play, but the cost of merging is still order n because we haven't parallelized the merge. So what does this solve into? Well, because the cost of merging will dominate and it's going to solve to order n. So the parallelism in my problem, which is the serial work divided by the critical path, is pretty small. The work is n log n, and the critical path or span is order n. So I have only log n parallelism. And as you know, log n is, it's not that small for a large data set, but for today's parallelism limits, given that how many cores we have and the GPU's parallelism, it's very small. So we need to parallelize the merge step. How can we do that efficiently? It's actually another ingenious algorithm, I think. It's because you can describe it in one slide and spend a little bit of time analyzing it, and that takes more than one slide. But let's assume at some point in the recursion, I have 2 lists that I need to merge, and they're not necessarily of the same length. Or they can be the same length. I'm just saying one of them is larger or equal to than the other. It covers all possible cases. So this is a very general statement. And I'm going to choose the median in the large list. Let's call the median element is at the location MA. So all the elements on the left is smaller than A of MA, and all the elements to the right is larger or equal to A MA. And then I'm going to do binary search on this other list, the list B, to find where I would have inserted AMA, the A of MA. And it returns me a location, very simple. You can call STD lower bound to find this, which means anything on the left of this location is less than or equal to A of MA that I searched, and anything on the right of this location is larger or equal to AMA. All right, so recursively I can merge these because I know that everything here and here are smaller than or equal to A of MA, and everything on these sides are larger or equal to A of MA. And this algorithm will recursively merge these things. Now, this is clearly correct, but what's the complexity? How many elements I'm able to discard at each, or actually I'm not discarding anything because this is not a search problem anymore. I am creating 2 subproblems of different sizes. The question about parallelism is, are they balanced enough so that the solution of my recursion solves to something that I want. And that's what we're going to basically deal with. So what am I getting rid of in some sense? I'm not going to, again, the word to throw away is wrong because it's not really entirely true because I'm going to recurse in both of them. But I can say that this list is at least of size NA over 2. NA is the size of the list A. And similarly, the part that's on the left of the median of A is also the at least size NA over 2. Which NA over 2, since A was the larger of the lists, these subcomponents have at least size N over 4, which means each one of these recursions is recursing on a problem that is less than or equal to 3n over 4, 3/4, right? Because this part doesn't include something that is of quarter size, and this recursion doesn't include something that's of quarter size. And I'm not making an argument about what am I discarding on B. It can be as bad as possible in B. This binary search might return the first entry in B, and that's totally fine. The bounds will still hold. Okay, so the recursive merges are operating on lists of at most size 3/4. And that's basically the code of what we described. We do binary search, and we call p merge, and there's an implicit task wait. For those of you who remember the OpenMP tasks part, which I think I spent only 10 to 15 minutes, this is how you would write it. The ugly tasking syntax is such that you have to first create a parallel region, and then you have to create a single region, and then you can spawn off your tasks. Of course, we're going to core some base cases for efficiency. Like we said, probably when the data size gets small enough that insertion sort makes sense, we're going to do that. So what's the bound? Let's start with the critical path span bound. I have a problem of size n, and I'm not, at least 1/4 of them stops affecting the critical path. So 3n over 4 is the critical path recursion, and log n is the binary search cost. Well, okay, where does it lead us to? This leads us to the case where these things are comparable, surprisingly. This might not look like it, but the n to the log base 4/3 to the 1, because any base logarithm of 1 is 0. This is n to the 0, so it's 1, right? And which means the cost of combining and the cost of the recursion is asymptotically the same up to polylogarithmic factors, which is the log n. So what I'm going to do is I'm going to increment that polylogarithmic factor, the power of it, by 1, meaning the span will be log square n. So this is a more peculiar application of the master theorem, but you can convince yourself that is correct, or you can just write down and solve this, right? There's many other ways of solving this thing. You can do it by substitution. I suspect you've seen those in discrete math classes. Now, sorry, the work bound is a little hairy because I'm creating 2 subproblems, and I don't really know where they fall. All I can say is there is an alpha such that one of the the 2 problems are at most unbalanced by a factor of 3. And then there's the cost of combining log n. The part of the lecture that I'm probably not going to go over is that the one way to solve this thing is you can claim some guess that you have a good idea and try to prove it by induction. And that's what we do here. For example, we claim that we can solve this recurrence to linear time. And so the hypothesis is this is some constant times linear minus some other constant times logarithm. And these constants are positive. And assume that this is holding. And then figure out what constants will make that induction work. And if you go over this long by yourself, because there's no real point about this, that you'll see that by choosing C1 large enough, you can actually prove it by induction that this is going to work. And for the base case, you'll choose C1 to be large enough. Okay. And in fact, I suspect you can actually get away with just choosing the most adversarial case, which is say that alpha is 1/4, which would be the worst case found because anything else is more balanced, and see if it actually solves to order n. So what did we get? We have a work of linear time, which is matching the serial complexity. This is a work efficient merge. We have a span of log square n. So we have some reasonable parallelism. This is actually pretty large for a large data set. But we haven't solved the sorting problem yet. We only solved the merging problem. How can we actually sort now? Well, we have a parallel merge sort that we're recursively calling. And the whole parallelism in this parallel merge sort is, again, this recursion part. The fact that we're creating these parallel merge tasks that are called recursively and by each processor. So you're creating a different task and spawning it off. So these merge sorts are running in parallel. And the final merge itself that is called on two sorted lists is also parallelized with the way we described. The work here is nothing different than the initial case, two subproblems and the linear time cost of merge, which will solve to n log n, as we know by now, because we've seen that recursion at least 5 times. How about the span? Well, the span is, we're again, since we have infinite processors, only one of them will impact the critical path. So we have n/2 from the recursion. And the cost of combination is we know the span of p merge, which was log square n. So we got this formula, which is almost like the span of merge, because remember the log base. This is not right. I'm gonna the top case needs to go to 1. So log to the base 2 to n. This is gonna go to 1, and then the cost of combining log square n will be the same up to polylogarithmic constants to n to the log base ba, and which means that we have to increase the power of logarithm, and it will become log cube of n. It's funny, you can find bugs in the slides after the third iteration still. And then the parallelism means n over log square n. It's identical, surprisingly, simply because the work is increased by log n, the span increased by log n, the parallelism is identical to the parallelism of merge. So we basically are done with shared memory parallelization aspects, and we're gonna move on to distributed memory. Any questions so far? Looks like this has been a very non-controversial lecture. Hello, after a brief disruption, let's get back to the end of the last part of our lecture, which is sorting in distributed memory. So far we have seen searching. Then we started with the serial searching algorithm. We did sorting in shared memory and focused on the merge sort algorithm where we needed to parallelize merge. In distributed memory, as you might remember, things are a little different because we have to actually ask the question, where is the data and how does it get, who owns the data, because the processor is different and sit in different memory spaces. So they have to get the data into their own local memory. And the algorithm we're going to describe is, I'm going to start with a simple version of it, which is a bucket sort. Here, this is a very successful algorithm if your input is uniformly distributed. The keys that you're trying to sort are uniformly distributed. Now imagine if that's the case, where your ranges between A and B with the keys uniformly distributed in that range, and you can just choose some number M, which is your bucket size, and just linearly scan the input and put entries into buckets. And then sort the elements in the buckets separately. So if things are uniformly distributed, you expect N over M elements roughly in each bucket. So sorting each bucket would take N over M times log N over M. So the initial cost of order N is actually going to be the determinant of the runtime. So this is actually a fairly fast algorithm if the assumptions hold. And how can we parallelize this algorithm? It's very simple as well. You just have to choose the M bucket size to be equal to the number of processing elements, whatever. In distributed memory, this can be the number of processes, number of cores, number of nodes if you're doing in-node multi-threading, and so on. In this case, each processor has a range of values it's responsible for. So initially, we have the data divided into N over P arrays. Nothing is sorted yet. All we have to do is locally run through our local list of this N over P size and assign each element to an appropriate bucket, in which case that is their destination processor. And we do a big all-to-all where these data is sent to their appropriate processors, and they will locally merge or sort them. In fact, they have to sort them. They can't merge them because we don't initially sort our inputs. So that could be a variation of the algorithm. And that's going to be it. That's very simple. And if the data is in fact uniformly, the keys are uniformly distributed initially, then this algorithm would work fine. And I encourage people to use this if your data is that special case. However, that's an unrealistic assumption for the general case. So this creates a lot of load imbalance and would likely perform very poorly in practice. So what's the solution? The solution is to choose pivots correctly. So this is really a generalization of quicksort. Remember, for those of you that know computer science well or have been paying attention to the beginning of the lectures, quicksort just chooses one pivot, one essentially random element, and splits the data into two classes and recurses. Now we have P processors. It makes sense to choose P pivots. In the terminology here, they're usually called splitters. We need to choose P splitters. And I'm going to describe the algorithm using M instead of P, because we would like the algorithm to be general enough so you can choose the number of splitters to be larger than the number of your processors, smaller than the number of processors. You can do over decomposition. Usually making them smaller than the number of processors don't make too much sense, but making them larger might make sense for certain over decomposition cases. So let's think about M as an abstraction, just like we start with bucket sort with M. The splitter selection will divide the list of N elements into M blocks, each one of them N over M, and we'll sort each block using some sort of quicksort. Now, the algorithm we're going to talk about is called parallel sorting by regular sampling. And the keyword here is regular. There's no randomness here in the sense that we are basically choosing equally spaced elements. And it's going to be obvious with the next picture. And the scheme will guarantee that the number of elements that is ending up in each quote unquote bucket is no worse load imbalance than by a factor of 2. And asymptotically, a factor of 2 is just fine to prove things. So let's start. You have a list of N elements, and each processor has N over M pieces of it. Again, I'm abstracting the processor count to M. So we are regularly choosing regularly spaced M minus 1 samples from each local list. Local meaning local to the processor. So that means we have a combined sample size of m times m minus 1. Okay, and then from that list, we're gonna do global splitter selection by also some regular sampling after sorting these samples or merging them if they're sorted, and then use that thing as my splitters and redistribute the data, my pivots, so to speak. And the thing to focus on this slide is the following, and it's going to be useful when we're proving things. If I am locally sorting my array of length n over m, and I am choosing regularly spaced m minus 1 samples from each local list, my first sample is larger than n over m squared elements. Why? Because the local list is n over m, and I am larger than 1 over m of it, the way I chose the sample. So this entry is larger. And similarly, the entry here, 9, is going to be larger than n over m squared elements, larger or equal to. Again, and larger or equal to the same for the other samples. So that's a little bit of an important detail, which basically also resolves one mystery, which is that how many, how do we combine these things? You don't need to actually resort them because we initially choose these samples from a locally sorted array, then they will come sorted. And all we need to do is a p-way merge here. Sample combining can be done by merging as opposed to sorting from scratch. So here's another way of looking at it. We sorted the local blocks. We picked m-1 regular space samples. We merged those samples into a single processor to form Y. And now the way we're going to choose our final splitters is, again, we are choosing these final splitters from a sorted Y. So this is initially how they come, and we merge them, the locally sorted pieces, and we come to this list of samples that are combined into a sorted form by merging. And now I'm going to do another regular sampling, and I'm going to choose every m over second element. So what is that? Sorry, I start with the m over second element, and then I choose m plus m over second element. And then I'm going to choose 2m plus m over second element. Once again, there's no randomization here. I'm regularly sampling from this list. Okay, and once I do reshuffling based on these splitters, so I chose these elements ym over 2, ym plus m over 2 are my final splitters. And those are going to be used to reshuffle my data so that's going to determine what elements are going to go to processor 0, processor 1, and processor 2. How load imbalance can that assignment be? And that's really the question I want to answer. So let's look at it. PI, after this splitting, will get the entries such that the processor I processor will get all sorts of entries xi, and they will be within this range, within this tight range, because that's the way I chose my splitters, right? Think about processor 2. Processor 2 will have entries that are larger than ym over 2 and smaller than m plus m over 2. And by symmetry, you can actually rewrite this yi minus 1 m plus m over 2 this way, because, you know, with the assumption that there's a total number of m times m minus 1 samples, instead of counting from the beginning, I'm counting backwards from the end. So I'm just rewriting the same formula, which is nothing that crazy. And the key thing here is each sample that I used is my splitter. Sorry, each sample yi, forget about splitters. The samples that I chose the splitters from are larger than at least n over m square elements of the whole list. And we know this because of this little picture, right? Each one of these splitters that I chose are larger. Sorry, not the each one of these splitters. Each one of these samples I chose is larger than n over m square elements. Okay, that's all we need to actually know to prove certain bounds. So if that is the case, then what do we know? We know that the splitter we use, which is yi minus 2m plus m plus 2, is larger than however its index times n over m square elements of x. Why? We know the samples we chose from, the samples that constitute the array y, all these samples that are here. Each one of them is larger than n over m square elements. And then we sorted them. With this sorting, I know that the first element is larger than n over m squared. While the second element is also itself larger than n over m square elements. And by cumulative impact of the previous element being n over m squared, the second element is larger than 2 times n over m square elements. Because again, this is sorted. I am larger than the elements that come before me, and each one of the elements that come before me are larger than some n over m square elements, and there is no overlap. These are distinct elements that each one of these samples are larger than, right? And by that definition, simply I can just multiply them and see that this multiplication is going to be useful in a second. And I do the same argument. How many elements my upper bound, meaning each element that is assigned to processor I, how many elements that each one of these elements xi is smaller than, and that's the upper bound argument, the same formula, m minus 1m minus m over 2. I multiply this with n over m squared, and that's the upper bound. So what does it mean? Every element that's assigned to processor I are larger than this many elements and smaller than this many elements. So how many elements could have fallen into processor I is just we subtract the number of elements that we're larger than and the number of elements we're smaller than from the total set n. And you'll see that if you do this math, you are looking at 2n over m minus n over m squared, which is less than 2n over m. In the best case, we're expecting n over m elements for a processor. And what we proved is in the worst case, that can only be a factor of 2 off, which is not really bad. So notice that I haven't actually fully covered the case. There's 2 more cases. So I have covered the case where pi is, the processor number is not the first one and not the last one, anything in between. So it's p2 to pm minus 1. But the other cases, p1 and pm, are actually easier. The one in the middle is tighter, so I just proved that case. So in practice, the load balance is actually much better than 2x. So since I proved that the splitter method doesn't create load imbalance, then the bounds are somewhat easier asymptotically, right? We're only a factor of 2 off, and now I can go about analyzing this thing. But first, a couple of practical things. The size of y that I combined, the set of samples that I'm going to choose the final splitters from, is of size p times p minus 1. So that's essentially p squared. And one processor will essentially merge them, or everybody will merge them redundantly, unless I parallelize merge. So that's a little bit of a cost. It doesn't affect asymptotics much, but it has some memory impact. So at large scale, the thing that can go wrong is you can just do the math. If I'm sorting on 20,000 processing elements cores, and I assign one MPI process per core, well then, and assuming some certain size that each splitter is 12 bytes, then you run the numbers. Just collecting these p9 times p minus 1 splitters, not splitters, the samples is going to be, these are not the final splitters, these are candidates again. This is going to be like 5 gigabytes per core. That's already exceeding the limits of per core memory. One possible quick hack is use something we have already seen before earlier in this lecture, which is median finding. We know how to find the kth element. We can just go find the median using parallel selection. And what that's going to do is it's going to divide the data in half. And it not only is going to do that, it's also going to allow me to recurse on half of the processors. So I divided the problem into half, and I say if I started with 20,000 processors, now I'm going to recurse with 10,000 processors each. Well, the good thing about this is the size of these samples list is quadratic in P. If I divide my processor count by half, the memory of Y goes down by a factor of 4, and quickly it goes down after a couple iterations of this recursion. That, however, your memory issues where it's going to be resolved after a couple of recursion. And in practice, this works very well. And there are other alternatives. You can use exact splitters. We can try to work on parallelizing the merge without redundantly storing all of Y all at once in memory. Let's do a little bit of complexity analysis. We presented this algorithm in its full generality that allows you to choose M, the sample, the splitter size to be somewhat arbitrary, independent of P. But for analysis, let's set it to P. And initially, we sort elements, right, locally. That will require N over P, log N over P. Selecting P samples, regularly spaced samples, it's only order P. That's not a big deal. The time to all-to-all broadcast, again, since we are all-to-all broadcasting, P times P minus 1 elements is P squared. Then this is actually not an all-to-all broadcast because this needs to go into one processor. So we should call this either an all gather or a gather. So I'm going to correct this slide. The time to gather the elements is going to be order P squared. Internally sorting them by one processor or redundantly in every processor is the same. It's going to take P square log P time, simply because log P square is also log P. And selecting evenly spaced splitters takes order P. Then each processor can insert these splitters, the exact final splitters we decided to choose, the final splitters we chose from Y, insert into their local range by just doing P minus 1 binary searches for the complexity that's shown at the bottom. P times log N over P. Why? Because each block was of size N over P, and I'm doing the order P binary searches. And then the time to reorganize the data is N over P. So what we're looking at here is the local sort, the sorting of the sample list Y, block partitioning the data, and finally moving the data around. So there has to be, of course, alpha beta cost associated with communication. So just put that in your head that there's a beta times N over P plus likely an order P times alpha component for the reshuffling of the data, which is going to be something like an all-to-all. I didn't want to change the formula, but that's it. For further reading beyond sample sort and various other variants of these algorithms that work best in practice, you can consult these two references or the references that are likely citing them. Thank you for your attention. And next Tuesday, we're going to have Julian Borrell talk about computational cosmology, a rare guest lecture. We used to have many more of them, but Julian does a great job. So I encourage you to come to the lectures, and he's a very energizing speaker.